Now we are through with how to produce electricity. Now I want to look at electric circuits. Is that okay? Now, types of electric circuits. The first one is a closed circuit. It's a type of circuit in which there is no gap along the conducting parts. There is no what? Gap along the conducting what? Parts. Look at this. There is no gap. From here is the battery. Positive. Here is the switch. It is closed entirely. So for that reason, the bulb lights up. We see there is a type of circuit in which there is no gap along the conducting what? Parts. That is, the key is closed. You can see it here, the key is what? Closed. So current flows through an external resistor. Example is the bulb, and it lights up. Are you getting it? So you have it that here there is no gap. It is closed. We call it a closed what? Circuit. There is no gap in between the wires, and that will bring about the flow of current all through the circuit, and the bulb lights up. Now the next is an open circuit. It's a type of circuit with a gap or opening along the conducting part. Look at the gap. It's a gap. It's not closed. Along the conducting parts, look at the parts. Along the conducting wires, they have the wires here. There's the battery, current flowing from here. But it cannot flow because there is opening. Here's a gap. Are you getting it? So this means that the key is open. You can see the key is open. In such a circuit, the battery maintains no current in an external resistor. It doesn't give any current to the external resistor. Example is the bulb or the load, such as the bulb. So the bulb does not light up. So here the bulb does not light up. So we call such circuits open what? Circuits, because the key is what? Open. Now the next one is a short circuit. It is a closed circuit which has no load on it. Closed, there is no gap, but there is no load, there is no bulb attached to it. Is that okay? The wires are connected directly to the battery. You can see the terminals of the wire connected straight to the battery. Can you see it? So there is no loads there. It's a closed circuit. So it's a closed circuit, quite alright, but short in the sense that there is no loads attached to it. Now, components of electric circuits and their symbols. What are the components? We have mentioned them. Number one, you have the cell. This is the symbol. This long line here, this is the wire connected, This long line here shows the positive terminal. Look at this. This is only one cell. Only one of them is called a cell. More than one, two of them combined together, we call it the battery. Is that okay? Now you can see this is the symbol. The longer line here shows the positive terminal, while this shorter one here, one that is shorter than this, is the negative terminal. Is that okay? Now the next is the battery itself. Battery will have its collection of two cells or two or more cells. Now you have the positive terminal, you have the negative. What follows now is what? Where is what's positive? It's supposed to be longer than this. Here is positive, and the shorter one is what? Negative. Are you getting it? Note that a cell is a chemical device that changes chemical energy to electrical energy. It generates electric force which drives electric charges around the world, a circuit, while the connection of two or more cells is called a battery. You can see it here, two or more. This is two. Here you have two here, two cells connected. Then one you have only one here, called a cell, while these two is called a battery. The third component of the electric circuit have the resistor. I have shown you today the image of the resistor, but it is the symbol of a resistor. Then you have variable resistors. Example is the rheostat. We use this symbol to represent it. You have seen before now the image of a rheostat. Now number 5 is plug key. or switch. We have seen the symbol before now of a key, but this is the image of the key we're talking about in electric circuit. In your laboratory, this is what you see as a key, plug key, or the switch. Now, earth connection. This is the symbol we use to represent it. But this earth connection, normally in the houses, is connected from what is called lightning conductors down to the ground. Are you getting it? It's buried into the ground so as to conduct away charges that will accumulate in your house and bring about thunderstorm. So this is the symbol of it. Now we have what's called capacitors. This is the image of capacitors, while this one is the symbol of it. They are all found inside electric circuit. Now this is the bulb. We use the symbol to represent the bulb. The bulb you see also in your houses. They'll have the voltmeter. This is just the timing. This is just the wires connected to it. But this symbol generally shows you the symbol of a voltmeter. You can see here is the voltmeter. This is what we call the voltmeter. You see it in your laboratory. Then we'll have the ammeter. This is also symbol for what? Ammeter. Look at the ammeter. You can see it. It measures current flowing into the circuit. It measures the what? Potential difference. That is, the voltmeter measures the potential difference, while the ammeter measures the what? The current flowing into the circuit. Now you have the galvanometer. Also measures, no matter how small the quantity of current passing through the content is, it can detect it. It detects small, very small quantity of current that is flowing through the electric circuit. So the galvanometer is used to detect it, no matter how small it is. Now we have the connecting wires. We use this symbol to represent the wires. Already you know what is called wires, which you see in your homes. Now electric circuit diagram. You can see now how it is being connected. Here is the cell, the positive terminal, the negative terminal, the cell. Now ammeter connected in series directly after it. So as to measure the real, the accurate quantity of current flowing through the cell to the whole circuit. Now you have the resistor. You have the voltmeter measured across the resistor to know the quantity of opposition that it offers to the current passing through. Now you have the rheostat, which is used to adjust the current coming into the circuit. And then we'll have the connecting wire. Connecting wire. Have this from here to here. Connecting wire. Connecting wire. While you have this as the key. Is that clear? Since the ammeter is a low resistance instrument, it is always connected in series in a circuit so that the quantity of current it measures flows directly through it without any alteration. I get it. So it's always connected in series. And after the battery unit is connected, it is of low resistance. Is that okay? It's always connected in a circuit such in the way that the quantity of current it is measuring will flow directly through it without any alteration. Are you getting it? Because if you have something like a resistor in between, it will be able to resist the current flowing, and you will be able to measure the accurate amount of current flowing from the battery into the circuit. Also, voltmeter is always connected parallel or across the 2 points where the potential difference is required to be measured. For instance, you have in the last diagram that this is connected between this is the resistor offering opposition to the flow of current. You can see the ammeter connected directly from the battery down here so as to measure the accurate amount of current coming from the cell into the circuit. Now this is connected across this resistor to measure the amount of opposition to the flow of current that it gives to the flow of what? Current. Are you getting it? So it is always connected across the 2 ends of this what? Resistor, for instance. For the resistor here, from here you'll be able to measure the potential difference, or you'll be able to measure the opposition that it what offers to the circuit. Now, electrical conduction through materials. Through what? Materials. Materials offer a certain degree of opposition or resistance to the flow of current through them. Materials through which electricity can flow easily are known as conductors. We have said it before now. They allow current to flow through them easily. So such materials, we call them conductors. We call them what? Conductors. You have, for instance, you have your stainless steel plates, a flat plate, or it could be the ball plates. Such materials conduct or allow current to flow through them easily. So we say materials through which electricity can flow easily are known as what? Conductors. The base metallic conductor is what? Silver, followed by what? Copper. So the base material, the base metallic conductor is known as what? Silver. And it's followed by what? Copper material. Most connecting wires and electric cables are made of copper because copper is less expensive than what? Silver. Is that okay? So you see some wires, connecting wires or electric cables. They are made up of what? They are made of what? Copper. They are made of what? Copper. Because copper is less expensive than what? Silver. Other conductors include human bodies. That is why if you put your hands, if you use your hand to hold a boiler and it's plugged and it is switched on, definitely it will shock you. But your body allows current to flow through it. So your body is what? A conductor. Other conductors include human body, salt solution, the earth itself. So the earth itself is what? A conductor. It allows current to pass through it. That is why in an environment where you have naked wire and current is flowing through it, such environments, once you match your leg on it, it shocks you because that environment is electrocuted. So it allows current to pass through it. It's an example of a conductor, and so on. Also, some materials do not allow current to pass through them at all. They don't at all allow current to pass through them. Such materials are called insulators. They're called what? Insulators or poor conductors. Example, plastics. Example is what? Plastics, dry wood, glass material, and so on. The examples of what? Insulators. Materials that have little properties of both conductors and insulators are called semiconductors. I've said it before. An example is the silicon. That takes us to Ohm's law. A German scientist, George Ohm, investigated the linear relationship between current passing through a wire and the potential difference between the ends of the wire. He was able to find out how the current that is passing through a wire is related to the potential difference between the ends of the wire. This relationship is known as Ohm's law. Is that okay? The law states that the potential difference across the ends of a metallic conductor, example is a wire, is directly proportional to the current passing through it, provided temperature and other physical conditions of the conductor are kept constant. This is known as Ohm's law. Now, the law is saying that the potential difference across the ends of the metallic conductor is directly proportional. What does that mean? The more the potential difference across the ends of this wire, the more the potential difference, also the more the current passing through it. Are you getting it? Provided temperature and other physical conditions are kept what? Constant. Is that clear? Okay, we want to see how we can represent this mathematically. Now, mathematically, we have Ohm's law written as V is directly proportional to I, where V equals to potential difference across the ends of the wire, and I equals to current passing through the metallic conductor. And from the formula, we'll have it that normally in mathematics, if you want to remove this symbol of proportionality, you introduce an equality sign, which you have here, and what a constant. If it had been mathematics, we would have put K. But the constant we have here is R, known as resistance of the what? Conductor. That is the opposition to the flow of currents that the conductor gives to in the circuit. Now we have it as we have V is equal to Ri, but it is not commonly written as V equal to Ri. Instead, V equals to what? IR. Is that okay? Now from here, you can now make R switch to the formula also, in case you're asked to calculate the resistance in this offered by this conductor. You have it that from here, R is equal to V over what? I. If you want to make R switch to the formula, from here we'll have it that V is equal to V over I equal to what? R. Because if you divide both sides by I will cancel out here, remaining what? R. So V over I gives you what? R. If you want to make I straight to the formula, you divide through by what? R. Meaning if you have divided by R here, cancels out. Divided by R here, so we'll have V over R equal to I. Are you getting it? So that is Ohm's law, defined mathematically. Now, materials that obey Ohm's law, that is, V is proportional to I, meaning that the more the current that is flowing into the circuit, the more the potential difference between the ends of the wire. So materials that obey Ohm's law are called ohmic substances or ohmic materials. Examples are pure metals. Are what? Pure metals and alloys. While materials that conduct electricity but do not obey Ohm's law are known as non-ohmic what? Substances. Quite alright, they conduct electricity but they do not obey what? Ohm's law. They do not obey the formula that V is directly proportional to I. So we'll call them non-ohmic what? Substances. Examples, we have electrolytes. We have what is called diodes. We have what's called transistors, rectifiers. These are also electric circuit components. We have the diodes, we have the transistors, we have rectifiers. They are known as non-ohmic what? Substances. Now, experimental verification of Ohm's law. We're having the circuit diagram here to represent this. We have the cell, have the ammeter connected directly after the cell. You have the resistor that offers opposition to the flow of current. You have the voltmeter that we use to measure the potential difference between the two ends of this wire where the resistor is fixed. We'll have the connecting wires down to the key, and then we'll have the rheostat, which is used to adjust the current flow. Now, how can we use this to verify Ohm's law? Are you following? Set up the circuit as shown in the diagram above. Like the diagram we just finished explaining now. Close the key and vary the current in the circuits by adjusting the rheostat. You close the key and you now adjust the amount of current flowing into the circuit using the word rheostat. Record the ammeter and voltmeter reading for each rheostat adjustment. The current flowing to the ammeter you record. For each rheostat adjustment, you check the amount of current read in the ammeter and that of the voltmeter. Record the ammeter and voltmeter readings for each rheostat adjustment. Obtain at least 5 different values of I and V and tabulate your readings. You obtain at least 5 different values of I, that is the current, and your V is potential difference, and tabulate your reading. For the voltmeter, the voltage there is measured in volts. And for the current, which you take the reading with your ammeter, I is the current measured in ampere, and then your resistance, you have it in ohms, which is now V over what? I. Is that okay? Now, in the graph of V, this one, all the values you have, about 5 values, is plotted on the vertical axis against I, the values you have read from your ammeter on the horizontal axis. So when the graph of V is plotted on the vertical axis against I on the horizontal axis, are you getting all the values you have read from your ammeter? About 5 readings you take from your ammeter, about 5 readings from the voltmeter at each rheostat adjustment you make. So you plot the values of the potential difference on the y-axis, the values of the current on the x-axis. It is found to be a straight line graph passing through the origin. So you're going to have a straight line graph from the passing from the origin. It must pass through the origin. Now the slope gives you change in the volts, the change in volts or change in potential difference over change in current. So have change in V over change in I, and that gives you your resistance. Is that okay? Now, while carrying out this experiment, there are precautions you must take to ensure accurate reading or accurate reading. So precautions which must be ensured to obtain accurate results. Number 1, ensure tight connections of the wires. They must be tightly connected, otherwise current will not flow through in the circuit. You must ensure tight connections of the wires. Number 2, avoid error due to parallax in taking readings from the ammeter and the voltmeter. You don't bend to the left or to the right while taking the reading. You take the reading straight with your eyes straight on that point. You don't miss, so as to avoid error due to parallax. We have discussed this error due to parallax before now. Ensure that the ammeter and the voltmeter do not have zero error. It could be that the pointer is after 0 or before 0. That is what you now say it has 0 error. Ensure that the pointer of the ammeter of the voltmeter is directly on at the point you have to take the reading. If it is from 0, at 0, you let it be at 0 before you start taking your reading. Is that okay? So at 0, you don't have to let the pointer be at there before you start carrying out the experiment entirely. But if it is behind 0 or ahead of that 0, it has 0 error, and you have to correct it before you carry out the practical. See, ensure that the ammeter and the voltmeter do not have 0 error. If there is, it should be corrected before using the instruments. Otherwise, you'll be taking the reading you'll be taking that will not be correct at all. It will not be accurate. You should use low current to ensure that the wires do not get too hot. Don't use secondary cells. Don't use accumulators because it will give the current it will give will be too much for that circuit to carry. So it will be too hot on the wire. So you can use 1 cell or 2 cells, 1.5 volts each. That will not give you much heat to the circuit. So you should use low current to ensure that the wires do not get too hot. You should also remove the key when you are not taking any reading with voltmeter or ammeter. Otherwise, it will run the battery or the cell down. So you must remove your key when you are not taking any reading with voltmeter or ammeter. Is that okay? Now, I want to look at connection of resistors in a circuit. How do you connect the resistors? When resistors are more than one in a circuit, they can be connected either in series or in parallel. Meaning when you have more than one resistor, you can connect them either in series or in what? Parallel. We want to know what it means to connect resistors in series. We mentioned connection in series or in parallel. We want to start first with connection in what? Series. When two or more resistors, you have R1, R2, R3. R there represents resistor. So the first one, the second one, the third one are connected end to end. This resistor one, the end of it. Look at the end here. So this end is connected to the end of these two. Are you following it? When two or more resistors R1, R2, R3 are connected end to end in a circuit, it is said to be in what? Series. So you have this end of R1 connected to the first end of R2. The last end of R2 connected to the first end of what? R3. So we see that such is series connection of resistors. The effective or resultant or total or net or overall resistance offered by these resistors now given by R equal to R1 plus R2 plus R3. This more than 3 can continue for this. Now we'll have this to be total resistance or net resistance or overall what? Resistance. So we have the formula R equal to R1 plus R2 plus what? R3. If you have more than this, you can add them. So to prove this formula we have here, we have seen already the circuit diagram of resistors in series. You have R1, R2, you have R3. The following you have V1, V2, V3, meaning the voltage across each of the resistors. Is that okay? And then you have this V here giving you total total voltage in the circuit. So to prove this formula we have here, we want to check the next page. When resistors are connected in series, there are points you have to note. Number one, that is that the current in each resistor is the same. The current is what? The same. And each is equal to total current supplied by the source, that is the battery. So in that one, I1 is equal to I2 and is equal to what? I3. Meaning the I1 is for resistor 1, I2 for resistor 2, and I3 for what? Resistor 3. So the current passing through each of these we say is the what? The same. And is equal to total current supplied by the source. And remember that in Ohm's law we have it that I is equal to V over what? R. It's from Ohm's law. We have that I is equal to what? V over R. That gives you the total current supplied in this circuit. So we'll have this diagram here, I1 for R1, I2 for R2, then I3 for R3 in series. Now also you note that the PD or the voltage is not the same across each resistor. It's not the same. Therefore, PD between point X and Y is the sum of the individual potential differences across each resistor. So V total there will give you V1 plus V2 plus what? V3. See, the voltage in each of the resistors here is not what? The same. So to get total voltage, you have to add the voltage for resistor 1, the voltage for resistor 2, and voltage for what? Resistor 3. So where V is equal to IR, that is Ohm's law. So if you now want to get the total V, you have V is equal to I1 R1. Then you have plus I2 R2 plus I3 R3. That gives you total voltage or total PD in what? Series. And since I1 is equal to I2, as I have said here earlier on, since I1 is equal to I2 and is equal to I3, is equal to total I supplied by the source for series arrangement. So you divide both sides of the equation now by I so as to get the value of R. So we will have here I1, I2, I3 is equal to I. So wherever you see I1, instead of putting I1, you put I. Whenever you see I2 is equal to I itself, I3 is equal to I. So you can see IR is equal to IR1. Instead of having I1R1, you have IR1 plus IR2 plus IR3. So once to now get the value of R itself, we divide both sides of the equation by what? I. Are you following it? So I have IR over I is equal to IR1. IR itself is telling you that V from Ohm's law is equal to IR. So once you get that we have it that IR itself is what? V. I don't know whether I get what I'm saying here. IR is equal to what? V. So we'll have it that IR over I now is equal to IR1 over I plus IR2 over I plus IR3 over I. Such that if you now divide through, you have this I will cancel out the I here, now remaining R. So I here will cancel out the I will have here remaining R1. I here will cancel out I will have here remaining R2. And then this I here will cancel out this I here remaining what? R3. So R here now is equal to R1 plus R2 plus R3. That is what we have here. That is the proof of that formula we had in the last page. I would say that total resistance in series is given by the formula R equal to R1 plus R2 plus what? R3. Is it clear?